Hi, my name is Josh Haynes, and I'm a part of the team Everyone Else. I'll be going over my individual progress report for sprints 3, 4, and 5. My sprint 3 revolved around the frog monster. The user stories are as follows. As a frog, I want to collide with the gamer so that the gamer will die and the level will end. As a frog, I want to have a slight delay when moving so that the gamer can avoid me. And as a frog, I want to move in the direction of the gamer so that it appears that I'm chasing the gamer. For sprint 3, I'm only going to explain the child user story for the frog's slight delay when moving because it is a critical user story and the other two are either trivial or the functionality was changed in a later sprint. For this child user story, the frog must have a slight delay when chasing the gamer. The way this works is that the game starts when the gamer presses the spacebar. The animation logic is then processed. An evaluation is done to see if 1 second has passed. If it has, then the frog will determine which direction to go in and will move 1 tile space. If 1 second has not passed, then the frog will not move at all. For sprint 4, I continue the work on the frog's movement pattern and actually changed the way its sprint 3 movement worked to make it more dynamic. The user story is as follows. As a frog, if I run into a wall, I want to find a new path towards the gamer so that I can continue chasing the gamer. The user story was made possible by implementing a breadth-first search algorithm to find the shortest path towards the gamer. My implementation of this algorithm was adapted from a maze solver example that is listed at the bottom of this slide. Since our map is set up as a two-dimensional tile-based grid, we were able to assign each tile a number value on whether it is ready, unavailable, waiting, processed, or part of the shortest path to take. On the image to the right, the ones represent an unavailable space and the zeros represent a ready space, meaning that 1 is not a path that can be taken, but 0 is a path to take. The 5s show the shortest path. Our frog only moves every 1 second and only 1 tile space at a time. So each time the frog moves, it will evaluate the shortest path to take and will only jump to the first tile in the shortest path. Each time the frog tries to update its movement, it will reevaluate the shortest path again and repeat the process. This diagram describes the BFS algorithm at a high level. The process starts by providing nodes that the frog and gamer are located at. Then the grid is initialized by setting each tile as either ready or unavailable. The starting node, which is the frog's node, is set as a waiting status and placed into a queue. It then repeats the process of checking to see if the queue is empty, removes the first node in the queue, marks that node as processed, and adds all neighboring ready nodes into the queue. Once the queue is empty, a check is performed to verify if a path exists. If it does, then the nodes in the path are set to a path status, and the frog is set to the location of the first node in the shortest path. If there is no path that exists, then the frog's location doesn't change. For the 5th and final sprint, I implemented the teleport tile. The user story is as follows. As a gamer, I want to be able to step on a teleport tile so that I can navigate throughout a level. The teleport tile is set up in a way that allows the gamer to move from one teleport tile to another. The direction that the gamer is facing when it collides with the tile will determine which teleport tile the gamer moves to. To make this as dynamic as possible, the teleport tile was designed in a way that it has an up, down, left, and right corresponding teleport tile. Any level that contains a teleport tile must have, at minimum, 2 teleport tiles. If a particular level only has 2 teleport tiles, then a constructor option is provided to set up, down, left, and right for both of the teleport tiles. However, the option is left open if a level has more than 2 teleport tiles, and the level itself can specify each teleport tile's up, down, left, and right tiles by using the corresponding set function. And this concludes my individual progress report for sprints 3, 4, and 5. Thanks.